Okay, hello class. Welcome to our first lecture. Our lectures in here are going to mostly just kind of supplement the textbook chapter and your labs and everything else you do. So you have the basic, information that you need, but I'm going to, through lecture, add a little bit, go into some more detail in a particular part about a particular topic that might be more difficult or something where I can do a demonstration using rocks or I could draw images, something like that, something you really can't get just from the textbook itself. So today I'm going to go into a little more detail into a part of science literacy I think is very important. Getting information in chapter 1 of your textbook and the links and the videos in that chapter, as well as the reading for the lab and some writing on the lab itself. Between all of this reading, and I hope you are getting the sense that science is perhaps a little different than the general public tends to think of it, and maybe different than how you learned about it in grade school. A lot of students are intimidated by or claim that they are bad at science, when really science is just the best way we know of to find out how things in our world works. Shouldn't be too scary. Yeah, sometimes you use math, but math is just a tool. And we'll be using math in this course too, but it's a good way to find out some things. So you use science when you try to figure out all sorts of things, how a magician did a trick, or why your car won't start, or why the cookies you baked didn't rise this time. Scientists try to find explanations and solve problems, and you do that probably on a daily basis. So science then helps satisfy the natural curiosity with which we all are born, which we ask questions like, why is the sky blue? How did the leopard get its spots? What is a solar eclipse? With science, we can answer such questions without resorting to magical explanations. We could use real-world explanations that have evidence. To many, science may seem like an arcane, ivory-towered institution, but that impression is based on a misunderstanding of what science is and how it functions. So you already know, in fact, science, aside from just being something that like really smart geniuses do, we think of Einstein and Newton and all these people, it's something that people do all the time. And I have some pictures of more typical scientists in a second. But science affects your life every day in all sorts of ways. It can be fun and it's accessible to everyone. Hopefully you kind of understood that with the bouncy ball activity. You can apply an understanding of how science works to your everyday life. And that's really valuable, and I'll kind of show you how to do a bit of that too as we go. And finally, anyone can become a scientist, whether you're going to be an amateur scientist or a professional scientist. And so that's the picture here. I kind of want to, dispel this myth, and even people that I kind of respect, like Bill Nye, don't really help with this. But we kind of have the idea of a scientist as wearing a white lab coat, probably some old guy, wearing glasses, something like that. But the truth is, that's not really how we like to portray scientists. And of course, there are plenty of scientists that look like this and will look like this as they get older. But scientists are from all sorts of walks of life, all sorts of diversity. And, I hope that, you start to get that throughout the semester. So for instance, here's a picture of a typical scientist. This is Dr. Emily Cole, an exploration geologist who is working in a gold mine here. This is Brian Huber, a waterfowl biologist for the California Waterfowl Association, banding some nice, what kind of ducks? Oh, northern shovelers. That's a cool kind of duck. I like those. He's got the camo. I know some of y'all look like this. One of my friends, Dr. Josh Bondi, is a Shoshone American Indian, and he's a paleontologist at University of Nevada, Las Vegas, where he digs up dinosaur bones, which is pretty cool. Another friend of mine, Ashley Hall, is an educator at the Cleveland Museum of Natural History and a marketing director for the Shaker Lakes Nature Center, also in Ohio. And she just wrote a children's book and has a background in paleontology. She, all of her makeup and stuff, she doesn't really, a lot of people don't really think she's a scientist and don't take her seriously, but this is what scientists look like. A couple that you might be more familiar with, you might see these showing up on PBS. This is Dean Regis and James Albury, again, some young fellas here. They're both astronomers and educators for the program Stargazers, which you may see on PBS. And then Katherine Johnson well, she died recently, unfortunately, but she almost single-handedly sent us to the moon. So she was able to do calculations that a lot of other people were not able to do, and was able to send us to the moon in 1969. So some pretty cool stuff. There's always been people kind of breaking the barriers of what scientists look like and what scientists are, who scientists are. And we're more accepting of diversity now than ever before. So, so anyway, I hope you feel welcomed, no matter what your background is. And so you already know quite a bit about the scientific process. And my textbook chapter goes into a lot more detail and gives some good examples as well. The pizza example with Neil deGrasse Tyson, I think, is a good example of how we can use science in our everyday life. So what I want to focus on today is to help you evaluate claims in your everyday life for accuracy. So we are constantly being bombarded with messages of which we should be skeptical. And so we got to think scientifically about the messages that we are getting. So things like, pork raised without GMOs. Well, cancer researchers discover new hope. Major petroleum company acknowledges reality of global warming. Clinically proven to reduce the appearance of wrinkles. I'm getting a lot of these ads lately. More recently, of course, and more topical, hydroxychloroquine cures COVID-19. So these aren't exactly the types of headlines that you'd find in a scientific journal, but they are examples of scientific message that one might encounter every day, especially being online. You're going to hear some things. How do you know if it's accurate or not? How do you know whether there's something you should pay attention to or not? So media representations of science and science-related policy are essential for quickly communicating scientific messages to the broad public. However, some important parts of the scientific message can easily get lost or garbled in translation. And so understanding science in your everyday life can help you to separate science from spin, identify misrepresentations of science, and to find trustworthy sources for further information, to continue to read further, learn more, see what's really going on, what's at the heart of the knowledge here. So to demonstrate how this works, we'll look at a set of questions that you can use to get to the science behind the hype. What is the source of this message? And does that source have an agenda or a goal? I thought this was a good cover because it mentions astrology down here, has a few things, are these some of these scientific claims, but astrology, of course, not science. Astronomy is different, but so an original piece of scientific research may be interpreted many times over before it reaches you. First, the researchers will write up the research for a scientific journal where they get into all the actual methods that they do, so those methods can be replicated by someone else. The specific results, loads and loads of citations, loads and loads of pictures. But then all of that information can be adapted into a simplified press release, maybe posted by Smithsonian Magazine. This will then be read by reporters and translated yet again into a newspaper, a magazine, or internet article, and so on. And then, so it's trickling down. So just as in a game of telephone that you played when you were a kid, errors and exaggerations can sneak in with each adaptation. And we're also looking at, does the source have an agenda? If they want to sell a certain idea or not, then that's obviously going to have a big effect on what kind of information you get. A good example, I think, was one from UC Berkeley that they mentioned, was in 2004, an international group of researchers modeled the effect of predicted climate change, because reported that this amount of change might eventually cause 15 to 37% of a select group of terrestrial species to go extinct. It was simple, straightforward science. However, much of the press coverage that followed was both sensational and inaccurate. For example, The Guardian ran the headline, I guess polar bears is what we're worried about, but the headline, global warming to kill off 1 million species. Scientists shocked by results of research. I guarantee they weren't shocked by anything. We generally tend to know things as we're going into it. And 1 in 10 animals and plants extinct by 2050, which isn't at all what the research said. So if you're reading a paper, an article like that, you're like, oh, well, scientists are saying this and this, and then 2050 rolls around and we don't have all these animals extinct, you're likely to think, oh, well, scientists don't know what they're talking about. But remember, You're not reading the actual research, you're reading something that's been watered down and passed on. And that's what we do. And because we can't all read scientific journals all the time, just know that that's what's going on. So in fact, most newspaper reports got it way wrong, frequently suggesting that over 1 million species would go extinct by 2050, and not, as the science implied, that over 1 million species would be sentenced to extinction by 2050 and would actually die off afterwards, maybe decades afterwards. In addition, many websites picked up the story, and as one might expect, conservation-oriented websites tended to run more sensationalized versions of the story, while websites with an anti-environmental agenda tended to dismiss the story altogether and not even publish it, even though it was good science. So in this case, it's clear that the media source of the story made a big difference in the information offered to readers, while the science itself, the scientific article itself, was sound. So you may have seen this floating around on the internet, but again, don't, like anything in this class, I'm going to tell you, don't take my word for it, right? Like I'm reading Rainbow. Don't take my word for it. You can read about how they came up with this information, exactly what they did to, establish the how many facts, how much factual information a source had versus how little factual information, how many outright lies or exaggerations, things like that, and whether things tended to skew more liberal or more conservative. So this is a pretty interesting chart where things kind of in the middle here, pretty fair analysis, minimal partisan bias, and I was kind of surprised because there's a couple here that are kind of on the ends that I always kind of read, and I'm like, oh no, I want to stick more towards the middle. And then of course you can see where the extremes are. So again, check it out, see how they came up with this, but it can give you a pretty good idea of what sources might be better than others. So I think that's pretty helpful. So the source itself really can make a big difference because you guys aren't reading scientifically reviewed or peer-reviewed scientific articles. I'm not all the time either, unless it's about my specific field of study. Usually I'm just, I'm reading the same newspaper articles you are, the same internet articles you are. How do we evaluate whether it's, oh, that doesn't sound right, or, oh, okay, it looks like they're treating this information pretty fairly. Balanced reporting is generally considered good journalism, and balance does have its virtues. The public should be able to get information on all sides of an issue, but that doesn't mean that all sides of the issue deserve equal weight. Science works by carefully examining the evidence, supporting different hypotheses, and building on those that have the most support. So some ideas are backed by a lot more evidence or a lot more powerful evidence than other ideas. They shouldn't be treated the same. So in science, there's no such thing as fair and balanced. Some ideas really are more powerful and better than others. Some opinions, I guess, really are better than others. So journalism and policies that falsely grant all viewpoints the same scientific legitimacy effectively undo one of the main aims of science, to weigh the evidence. All that matters in science is the evidence and the amount of evidence. We don't have to be fair and balanced, we don't have to be unbiased, anything like that. It's all about evidence. And if you do have a bias, then eventually that'll be teased out. So we want to make sure not to show unfair balance. Also, we want to make sure, is the scientific community's confidence in the idea actually portrayed? So all scientific ideas, even the most widely accepted and best supported, like the germ theory of disease or basic atomic physics, are inherently provisional, all these ideas, meaning that science is always willing to revise these ideas if warranted by new, guess what, evidence, right? However, that tentativeness doesn't mean that the scientific ideas are untrustworthy, and this is where some media reports on science can mislead. So it's like, well, they don't know for sure because this idea is open to change, or it is being tweaked a bit, or it has been changed. And that doesn't mean those ideas aren't great. It means new evidence means we change our ideas. That should be one of the most powerful parts about any explanation. Sticking to the same idea despite new evidence showing you something different is not a very good way to try to find out how anything works. So a good example here, every few years, gene therapy makes a spotlighted appearance in the news, and for good reason. Gene therapy holds the promise of correcting genetic diseases at their source by replacing broken genes with working versions, but this is still largely just a promise. A 1993 newspaper article, for example, predicted that human DNA will be a major heart drug of the near future, with gene therapy a common treatment procedure, though such treatment was still unavailable as of 2007. So such sensationalized reports ignore the logistical difficulties of getting new genes to the cells that need them. Almost 30 years after the first rumblings about the possibility of gene therapy, the technique is still in experimental stages. And we're kind of thinking about that now with the COVID-19 vaccine. We hear about, okay, this one group's working on it, this other group's working on it, they're coming close to a good vaccine, they're starting a trial on 60,000 people soon. But to actually get through all the channels to make it out to the general public, that's a little bit longer down the road. So we don't want to show that science is really sure about something when they're not. And on the other hand, we also don't want to show that scientists are unsure about something when actually they're pretty sure. And a good example is human-induced or anthropogenic climate change, where there's really no controversy among scientists about what's causing the majority of our climate change today. Any controversy usually comes from non-scientific sources. So newspaper reports should be fair in how scientists are often unsure about a lot of things and also very sure about other things. So they need to be fair and report that, and they often aren't. So there are controversies in science. For example, physicists are currently in disagreement over the basic validity of string theory. And this is apparently a simplified version of string theory, which I have no idea what it is. String theory, though, is, let's find out, the set of key ideas that have been billed as the next big leap forward in theoretical physics. I don't know what it is, but it doesn't matter. It's a big idea. You've probably heard of it before, but physicists are really arguing about whether or not it exists. That's a real controversy. That's a fundamental scientific controversy. So yeah, there are scientific controversies. Articles can definitely talk about those. However, most controversies are blown out of proportion or misunderstood by the general public. For example, biologists have different views on the details of how evolutionary change occurs in species. This controversy focuses on an important aspect of the mode and rate of evolutionary change, but a change in scientists' acceptance of one idea or another, whether it happens very fast and with starts and stops, or whether evolutionary change is always really slow and gradual, would not shake evolutionary biology to its core. Scientists on both sides of this issue accept the same basic tenets of evolutionary biology. Another good example of this is this discovery recently of an animal called Ardipithecus. This is a primate. I think it must be a type of ape, and maybe a hominid that was discovered recently. And headlines say things like "New human ancestor makes evolutionary biologists question everything they knew about human evolution." You can probably see that a lot of creationists, jump on that. Oh, they don't know anything about human evolution. They're totally rewriting everything. And you often see headlines that say things like, "Study makes scientists totally question everything they knew about something," or totally rewrite everything they knew about something. That's never the case. That doesn't happen. Ardipithecus is a great puzzle piece in what we understand about the human evolution. It may make us question the dates of things, like, oh, Ardipithecus is maybe, 2.3 million years old, as opposed to where we thought this kind of ancestor would be like 1.8 million years old. Details like that. But they never really make us question the basic tenets of evolutionary theory. We need there'd be a tremendous amount of evidence that it would take to do that. And really, that kind of brings us to my next point. It takes evidence to make us question things, usually a lot of it. Controversies may exist between scientific and non-scientific ideas as well, such as evolution and intelligent design or creationism. But again, this does not reflect controversy within the scientific community, even if these arguments receive too much media time. We may all kind of remember, especially if you're into science, the debates between Bill Nye and Ken Ham of the Discovery Institute and the Creation Museum here in Kentucky, actually. I think if you haven't seen it, don't bother. You can if you want, I don't care. But it can kind of all be summed up with this. where what would make you change your mind? And Bill Nye says the absolute scientist answer here, evidence. If you had evidence of, what you're trying to say, then hey, I'd change my mind. We can't be married to an idea, though, we often are very passionate about what we're working on, but a hypothesis needs to change if evidence warrants it. However, Ken Ham, not surprisingly, says nothing. Nothing would make you change my mind. Anything you come up with would not make you change your mind. And that means that he's not thinking, surprise, surprise, scientifically. So that really kind of gives us a good idea as to what scientists need to do. We need to accept evidence and use that to create new ideas and to develop and change our old ideas. And that's the part about science. If it all stayed the same, like what people knew about evolution or anything from the 1860s, well, we wouldn't know anything about genetics. We wouldn't know how to cure diseases. We wouldn't know anything. So yeah, all of our ideas change over time, even if the origins of those ideas are quite old. Okay, so, and then our last one. Okay, always find sources with scientific expertise. And this is tough, especially when you have a lot of websites that have the word science in the heading. It can be really difficult. But try to find websites produced by a research institute, a governmental body, that can usually be pretty good, a respected educational institution, or a major scientific association, like the American Psychological Association, the United States Geological Survey. We'll be reading some things from them throughout the semester, stuff like that. These sorts of organizations are all key parts of the scientific community and have an interest in accurately explaining scientific issues, not selling you something or trying to convince you of a certain idea. For example, the Centers for Disease Control, CDC, we know, the American Association for the Advancement of Science, the USGS, like I mentioned, the United States Fish and Wildlife Service, or Nature magazine, or Science magazines, a good one too, are all trustworthy sources. Avoid ulterior motives. So try to avoid those websites that may that stand to gain from biasing the information presented, like a lobbying or advocacy group. And also keep the research current when you're looking at information. Science is ongoing and is continually updating and expanding our knowledge of the universe. Scientists publish many hundreds of papers each year on areas of active scientific research. If I was going to cite a study on human-induced climate change or fossil fuels or anything like that, the amount of carbon dioxide in the atmosphere and predictions for the next 50 years, I'm not looking at a paper from 1990. I'm not looking at a paper from 2010. So much is published on this topic, so much research and active work is being done. I'm going to look at a paper from the last 2 years. Now, it depends on what I'm looking at. If I'm looking at a paper on the anatomy of Tyrannosaurus rex, I could probably go back to a paper about 20 years old because there just aren't as many people doing research on dinosaurs. Check for citations. Scientific publications generally give credit to related research by providing a list of citations. You can't keep citing yourself either. You see that in a lot of pretty biased publications where they just have a whole list of papers or books that they wrote. You need a diversity. Science relies on diversity. So you look at those citations, you can dig in and read them, and you can study those references, and you can double check the website's validity, or even dig deeper into the issue if you're interested. If you're like, okay, now what does that paper actually say about this? Let me look. And you can often find it. There are more open access science journals now than ever before. So that's great. You can read all sorts of things. So finally, how strong is the evidence that you're looking at? So when evaluating a scientific idea, scientists carefully consider the relevant evidence, and you can too. You've read an article in a newspaper, done a little more research, uncovered several lines of evidence, and now it's time to weigh those data for yourself. Here are some questions to ask yourself as you consider the evidence. Does the evidence suggest correlation or causation? This is always a fun thing for science teachers to talk about, correlation and causation. So I have a chart here, a pretty classic example. Ice cream sales correlate with shark attacks. Now, does that mean that more ice cream sales are causing more shark attacks or vice versa? No, neither. They're both dependent on the same kind of thing. More people at the beach, hotter temperatures perhaps, all sorts of things like that. But they don't really have anything to do with one another, okay? So that's important to know. If we're seeing that there's a few trends that seem to correlate, okay, but what's really happening? We have to dig deeper. Climate scientists are all about this because they, really pay attention to this sort of thing. On kind of a lighter note, there was a page, it's called Spurious Correlations, where they say you'll just get really into data and graphs and stuff. And what they did was they went through all these different charts of all sorts of things, just bizarre things, and to see which ones match up. It's kind of a funny example of how correlation is not the same as causation. So, is the evidence based on a large scale of observations or just a few anecdotes? That's important too. If someone says, well, I took coconut oil and it totally got rid of, this and that, whatever's wrong with me. Okay, that's an anecdote. And the plural of anecdote is not data. But we need to look at longer term, bigger studies to really figure out what's going on. Evidence back up all the claims made in the article or just a few of them. You'll see this a lot as cherry picking evidence. Oh, this evidence suggested this, but then they ignore the evidence that says that something is incorrect. Got to make sure that they're treating all the evidence, that they're looking at and evaluating and all the evidence. Are the claims in the article supported by multiple lines of evidence? Just one piece of evidence isn't enough to suggest anything. You need a few independent, that'd be the preference, lines of evidence. And we'll get into that as we talk about continental drift and plate tectonics. Does the scientific community find the evidence convincing? So what does science say about the evidence in this article? Because things get published in journals that can be thrown out, that may not be that good of science. So what does science say about it? So these are all things you can look up because in today's world, it's more important than ever to dig a little deeper to evaluate the accuracy and intentions of statements made by people and sources, even those that seem like authorities. Basically, with science, don't take their word for it. Don't take my word for it. Like I like to say, today you have the sum of human knowledge on a small device you carry in your pocket. I grew up with the Encyclopedia Britannica CDs, or AOL.com came up with some CDs too with all this information. And that was like, whoa, we got all this information. That was before the internet. So then when we have the internet, it's like, whoa, we have all this information. So I grew up in a time where we treated the internet as an encyclopedia. And so I feel like, that means then that I have an idea that, okay, it's to use to find information. Of course, there's a lot of bad information out there. So that's why we need to be careful. So you have great power to understand the world. In fact, you have greater power to understand how the world functions than anyone else in the history of humanity. And that's pretty powerful, right? With that power, then, comes great responsibility, right? Like Spider-Man. So don't lose your brain out there. Keep your focus. Pay attention to what scientists think about things and think like a scientist. And I think you'll be in pretty good shape. So anyway, I hope that was helpful. We have an idea of how to evaluate some different claims and maybe feel a little more confident as you're reading things that you're bombarded with every day online. So thanks a lot, guys. Again, read the textbook chapter 1. That's where the most important information is on science and how science functions. I'm just adding some other stuff here about the nature of science and evaluating it in your everyday life. So it's all good stuff, all important stuff. You got some videos to watch as well. And anyway, I hope you enjoy, and I will be talking to you later. Thanks.